how we can go from something that's fairly simple, PV equals nRT, something you could handle as a sophomore, and then a day later, all of a sudden, it's exploded into this huge idea that explains all gases are just molecules in motion and their energy is related to the temperature of the gas. Just like that. Boom. And not only that, okay, so that's a phrase, but now we've got all this math we have to do on top of it. So what I wanted to do is to go through these more gas law problems. So it's in your packet. Find it. All right, good. And before I started today, I went back and was like, geez, so what formulas have they learned in the last few days? And why don't I walk you through? Maybe a piece of paper is good. Maybe you just chill. But right now, let's start with this. The ideal gas law, PV equals nRT. And the new form of it, given in terms of molecules, little n is for moles, big N is for molecules. Now, since N times R needs to be the same as big N times K, since big N is the number of molecules or atoms, that's a huge number. So K has got to be really small. Now, if we look at our values, these are two numbers that are given on the AP constant sheet. They'd be given in any assessment that you'd have to take, but you're going to memorize them anyways because that's the way you guys are. R is 8.31 joules per mole Kelvin, and K is 1.38 times 10 to the minus 23. This is known as Boltzmann's constant. Now, I'm a little embarrassed. I'm not sure if there's two N's or not. Look it up. Ideal gas laws. Boom. Now, the ideal gas laws we can utilize, and there's that derivation in the book talking about how pressure times volume. Let's just look at those units again just for a moment. Just for a moment. Pressure is, what is that again? Oh, yeah, newtons per meter squared. Volume is meter cube. Oh, do you see it? It's a Newton meter. Well, what the heck's a Newton meter? I'm not sure where I was going with that. A Newton meter is a joule. So P times V is actually a measurement of energy. Now, the internal energy of a gas, that's what U stands for. Internal energy is going to be 3/2 PV. But since PV is equal to nRT, or PV equals capital N KT, I could also write it in this form. Now, the internal energy of the gas is really just the sum of all the kinetic energy of all the different molecules or atoms in the gas. So by doing a little derivation that we worked on, I believe, last class, I'm actually shooting this in the future, sort of like when actors film something at the end of the movie before early. So I'm not sure but I think we did a derivation that's going to show the sum of all the kinetic energy is the internal energy of the gas. Now, we do a derivation, and we end up with two formulas for velocity. And we're talking about the root mean square. The reason is because there's all different velocities in a gas. This is the root mean squared, and it's sort of a mathematical artifact that when you take the square root of an average, that's what root mean square comes in. So there's two different forms we could use to solve for that. We have V root mean squared equals 3RT divided by M. Okay. Where R is 8.31, so that's like a number, an everyday number. M would be the molar mass, but this is the kicker. It's got to be in kilograms. So for oxygen, for example, for O2, it's 32 grams. I got to make that 0.032 kilograms. Tricky. Next, The other form, and I actually like this one better, is the velocity root mean squared is 3kt divided by little m. Now, k is a super small number, times 10 to the minus 23. So the mass is also going to be a super tiny number. And I think maybe we'll get into the example. We'll get into that with the examples. I kind of like this one better. All right. So with that all said, phew, it's brutal how we get there just like that. Let's take a look at number 1 together. Welcome back to chemistry. Number 1 says, a container holding 0.1 meter cubed of argon gas. Argon gas is argon in Brinkelhoff. No, because it's a noble gas, so you'd find it just in its form, Ar, argon, 1 atom. It's at a temperature of 30 degrees Celsius with a pressure that is given. It says, find the number of moles of argon. Well, if we were to utilize the ideal gas law, PV equals nRT, and I solve it up for n, PV divided by RT equals n. I believe we have enough information to solve it right here. So let's do it. Let's bask in the glory of how easy this is for you guys. P times V divided by the ideal gas law constant times the temperature. Oh, did you see what I did there? Yeah, it's got to be in kelvins. It's not a big deal. You guys knew that anyways. So, get your calculators out. What do you think the percentage of people that have their calculators out is at this moment? I'm going to say 33%. I end up with 9.53. Anybody else get that? Yeah? Good. All right. Thanks, Amanda. 9.53 moles. Boom. Moving on. Find the mass of argon. Now this is going back to chemistry a little bit. If we have 9.43 moles of argon, I can do my dimensional analysis. It gives me the molar mass of argon right there, 40 grams. So in 1 mole of argon, it's going to be 40 grams of argon. Now, I don't have to necessarily convert it to kilograms at this moment because it's really just looking for a mass. So take that. I know you already have the answer. Let me catch up with you. I got 381 grams-ish. How about, I'll write it as 381. Good. Find the number of atoms of argon. Yeah, that's not bad. All right. So, this is just chemistry review. If I've got 9.43 moles of argon, and I want to convert to atoms, if I have moles and I want to go to atoms, 1 mole has 6.02 times 10 to the 23rd atoms. That's right. It's just Avogadro's number. Turns out, though, that now that I'm looking at my calculator again, this is 9.53. 9.53. Which is what I used in my last one. Sorry. I got 5.74 times 10 to the 24. This isn't going well. Something tells me I'm not going to make it through this without making some major mistakes. Should have been 9.53. Oh, lastly, find the total internal energy of the gas. Oh, now we're getting somewhere. You haven't done this before. Well, energy could be calculated by doing 3/2 PV. Let's do that. So 3/2 times the pressure, 2.4 times 10 to the 5th, times the volume, 0.100 meters cubed, gives me an internal energy of... Now you guys should really have your calculators out. You're going to like fall out of shape here. You're going to go and try to punch in numbers quick. Your fingers are going to be all fumbling all over the place. I got 36,000 joules. Now, just for kicks, and if you want to fast forward this next part, feel free. You know, I can't see you. But if I go with 3/2 nRT, number of moles, I found that to be 9.53 times the gas law times the temperature. Now, would you do this if you were doing it on your own? No. Heck, you're not even doing it on your own anyways. But I just want to show off. Yeah, close enough. 36,000 joules. Okay. That was mostly chemistry review. Those of you that took AP chemistry, I'm not trying to insult you guys. I know that's not that bad. But some people here haven't seen this stuff since sophomore year. Think of who you had a crush on sophomore year. It was a long time ago. Well, it was for me. Number 2 says, a sample of an ideal gas is slowly compressed to 1/2 its original volume with no change in temperature. What happens to the average speed of the molecules in the sample? And what happens to the internal energy of the gas? All right, so it sounds like we have an ideal gas that is compressed so that its volume is only half as much. So, but then when it's compressed, it's all... Okay. So, how would I look at the change in internal energy? Well, oh, I need my glasses. Who am I kidding? Oh, it's asking for average speed. My bad. Average speed. So the velocity is the square root of 3kT divided by the mass. That's going to be the molecular mass, like for one tiny little guy. Now, let's look at, what factors change here? Well, it's a closed system, so M doesn't change. Check. K doesn't change. Does the temperature change? Oh, no, it says there's no change in temperature. So if there's no change in temperature, do you see it? Josh sees it. Nice job, Josh. Oh, wait, Josh isn't listening. He's fast forwarding this anyways. But the rest of you see it. If there's no change in the temperature, the average velocity would be the same. And when I say average in this case, it's really the root mean square. Good. What happens to the internal energy of the gas? Oh, well, this could be more interesting. Let's see. So U is equal to 3/2 PV. So if I wanted to do the change in internal energy, it could be 3/2 change in PV. Since, does it say the pressure? It doesn't say anything about the pressure. What else do I know about change in internal energy? Well, my other formulas, change in internal energy could be 3/2 NR change in temperature. Oh, do you see it? I know you do. Adam sees it. Thank you, Adam. Since there's no change in temperature, there's no change in internal energy. Now that's going to come into play a lot when we get into thermodynamics. Isothermal. This was an isothermal process. Let's write that word down. I would feel better. Isothermal, because the temperature does not change. the temperature doesn't change, the average speed of the molecules and the sum of all the kinetic energies also would not change. Now, I know right now somebody would be asking the question, well, wait a minute, how do we compress the gas and not raise the temperature? Well, the idea here, which we will get into a lot with thermo, is that you do it slowly. So that as you do it slowly, heat actually flows out of the system. Energy is transferred from the container into the environment. We haven't talked about that symbol capital Q yet, but we will. I believe they call that foreshadowing. Numero 3 says, a steel bridge spanning the Piscataqua in Portsmouth has expansion joints to allow for movement. How much expansion should the engineers design into the expansion joints if the bridge is 180 meters in length? Assume the winter temperature at its worst is negative 45 degrees Celsius. Yeah, it doesn't get that cold. And the summer temperature is 70 degrees Celsius. The coefficient of linear expansion for steel is given. Right now you're thinking, that's not a gas law. What the heck? But we did talk about this at the very beginning of the unit. And it turns out we hadn't really done any math examples of it yet. But I can say that the change in linear expansion is going to be equal to the original length times the coefficient of linear expansion times the change in temperature. It's pretty much just a plug and chug. I'm going to keep the units showing this time. So if we have a bridge that's originally 180 meters, and there's a coefficient of linear expansion of 12 times 10 to the minus 6, and it's basically per Kelvin, or 1 over Kelvin. And then the change in temperature, I'm just going to look at the temperature range. So the difference from minus 45 to minus 70, the difference is 100 and whatever that is, 15, right? The negative sign's not really going to matter. The change in the length, let's plug it in. I got 0.2484, or just about 0.25. All right. You guys cool with that? Look, it's not a big deal. It's a simple plug and chug. The relationship is given. When things get hotter, they expand. When things get colder, they contract. Boom. Number 4. Find the volume of a tank necessary to hold 5.8 kilograms of hydrogen gas, H2, at 293 Kelvin if the pressure is not to exceed 100 ATMs. ATMs? Come on. All right. In an effort to stall, I'm going to make a list of everything that I know. Not everything in life, just of this problem. So the pressure is 100 ATMs. The volume, that's what I'm trying to find. Temperature is 293 Kelvin. And it gives me a mass of 0.58 kilograms. All right. I know deep down that this is somehow going to tie back into the ideal gas law. And Avogadro's recognition that any gas, independent of what gas it is, the same number of molecules will be in the same volume at a given pressure and temperature. That's what this all comes from. So if I solve it up for volume, it's going to be nRT divided by pressure. Now to get the N, because it's been a little while for many of you, I'm going to do that separately. If you're advanced or you took AP Chem and you want to do it in one step, do it in one step. It's all good. If you're really just sitting there, like on your phone while I'm doing this, that could be happening. I don't know. See, if you were in class, I could yell at you. Just right now, somebody reached for their phone. Come on, Abel. Now, to find the number of moles, if I go with 5.8 kilograms of hydrogen gas. Now, hydrogen gas is going to be H2. So if I'm trying to go from kilograms to moles, I'm going to go moles to kilograms. Now, this may mess with you. Maybe I should do it in 2 steps. Hydrogen has an atomic mass of 1, about 1 gram per mole. So hydrogen atom. Hydrogen gas, H2, is going to be 2 grams per mole. So I'm going to take this and write it as 2 and then times 10 to the minus 3. Because that cancels out the kilogram. That's the same as going to 0.002, right? I know you know this. Let's do it up. I got 2,900 moles. Wow, that's a lot. Let's plug it in and get an answer. So I got 2,900 moles times 8.31 times the temperature of 293 divided by 100. Oh, that's 100 ATMs. I also have to remember that 1 ATM is equal to about 1 times 10 to the 5th pascals. All right. So it's going to be 100 times 1 times 10 to the 5th. See how easy it is? So number 4. We're on number 4. It's already messing with you. I got something that's not right. Divided by. Now you picked up your phone, didn't you? You could have picked up your calculator and plugged this in, like I am, working hard, or you could check your phone, as if anything is going on out there in the world right now. You're just reading the same thing over and over. Plug it into your calculator. I got 0.706. I don't know if that's right, but I'm in the middle of this take, and I'm not stopping. 0.706 meters cubed. I think it's time for me to take a short break, but then come right back. I don't think you need a break. I think you've been on break. Whew, we're already 23 minutes into this. We still got 3 more to go. Let's keep moving. Number 5 says a propane tank is filled with gas on a cold winter day when the temperature is negative 20 degrees Celsius. The tank was filled until the pressure gauge was 22.5 ATMs. The very next day, it began to get warmer, and the day after that, the tank was 35 degrees Celsius in the sun. What did the gauge read when the tank was so hot? Know what I'm going to do? That's right. Let's draw a picture. Here's the tank. I'm sure you could draw a better tank. I'm sure you could. I'm going to draw it a little smaller. I have enough room to fit in some information. So here's the tank. Boom. The first day. Here's the tank. Boom. The second day, when heat was added to the system by sitting in the sun. So the pressure initially was 22.5 ATMs. The volume, well, that's the volume of the tank. Does it give that? No, it doesn't. Temperature was 253 degrees Kelvin. Or 253 Kelvin. Now, pressure 2 is what it's asking for. The volume, it's the same. Aha. And temperature 2 is 308 Kelvin. Now, as I started this problem, I was trying to think about how am I going to incorporate PV equals nRT into this problem with the information that's given. And then I realized that I don't need to. I can say P1V1 over T1 equals nR. And since N and R are not changing, that's going to be equal to P2V2 over T2. Yeah, I just heard you guys say, oh, right. I get it. Now, since the volumes are the same, those cancel out. And you know what? Feeling like I'm just going to solve this up for P2. I could convert it to pascals, but you know what? I'm going to just leave it in ATMs. Why? Because I can do that. What are you going to do about it? $27.4. So 27.4 ATMs. All right. Why do I do that one again? Why? Because it's almost too easy. Because a lot of the AP problems are like that. Instead of having to really get into the calculations and knowing gas law constants and whatnot, a lot of times it's just a simple ratio. It makes for beautiful multiple choice questions. Number 6. 4.5 moles of oxygen gas are in a 0.031 meter cubed container at an absolute pressure of 3.85 times 10 to the 5th pascals. What is the temperature of the gas? B, what is the average velocity of the gas molecules? Hey, finally, we get to do one of those. All right, so I've got number of moles, volume, pressure. It's asking for temp. That seems pretty easy. Let's do it. PV equals nRT. So I solve it up for T. I get PV divided by nR equals T. Yeah, this is it. Go ahead, work on your own. I am going to take a break from my own voice. Did you get that? 319 Kelvin. Good. Now, what is the average velocity of the gas molecules? All right, let's do this. So the root mean squared velocity is going to be 3 kT divided by the mass of just one of the molecules. And I'm going to choose this formula this time. I prefer this. I do. So I have 3 times K, which is 1.38 times 10 to the negative 23rd. That's Boltzmann's constant. Times the temperature, which we just found to be 319, divided by the mass. Now, the mass of oxygen, right, O2 is going to be 32 grams per mole. If I just plug in 32 right here, I'm going to get a ridiculously small number. Ridiculous, right? And gases aren't moving that slow. They're moving hundreds of meters per second, even thousands. So that clearly is wrong. If I make it in kilograms, 0.032, does that do anything for us? No, it's still way too small, right? What I have to do is to take the molar mass, that is 0.032 grams per mole, or how about this? For one molecule, it's 0.032 atomic mass units. Now, one atomic mass unit is 1.66 times 10 to the negative 27 kilograms per 1 use. Those cross off. Because Boltzmann has joules in it, my mass has to be in kilograms. All right. Now this time, in all seriousness, get your calculators out. Plug it in. My back is starting to hurt from carrying you. Yeah, you, Nick. So I got a huge number. Oh, yes, but I forgot to take the square root. And I end up with 15,800 meters per second. Ooh, this gas is moving. 15,767, but I'm going to call that 15,800 meters per second. Now, I hope that's the answer on the bottom, because I'm not redoing this video. Oh! What the heck? What did I do wrong? What? Where did I go wrong? I know. I should have studied harder in college. That's where I went wrong. The heck did I do wrong, though? Seriously. Times 319 divided by 0.032 times. Is it not times 10 to the minus 27? I feel like it is, though. We're talking about oxygen gas. It's 32 grams per mole. I gotta push pause. This is where I'm just used to one of you bailing me out. Jack, I know you know. Tell me. What did I do wrong? Ah! You're right, Jack. You're right. You're right. Right here, I blew it. I blew it. I was feeling so good about myself. Like I actually knew what I was doing. And then I made the classic blunders. We all know from The Princess Bride, never start a land war in Asia. But number two, when converting from 32 atomic mass units into kilograms, one atomic mass unit is 1.66 times 10 to the negative 27 kilograms. Therefore, this number right here is just 32. And then when you plug it in, you end up with, I believe, now I need closure. Crap. Sorry, if your parents are listening, I apologize. They're not going to believe that I've made a mistake. This is so that they know this is the first time all year. The first time all year I've made a mistake up at the board or on video. If you plug it all in, you get 498 meters per second. Sorry about that, guys. Sorry. Lost my focus. This video is dragging on too long. Let's call it a day. Hope you guys are well. Can you go back, maybe look in the textbook on this velocity is the root mean square thing, and maybe you can set yourself straight. Sorry about that. Thanks, guys, for hanging in there. Hope you're doing okay.